So this, once again, that sequence that we did at the end. Just the same idea, illustrate one idea, but it is important. The uniform versus pointwise convergence. Okay, so once again, the uniform is on the right. So that distance that we have defined is that's the convergence we're considering on the right, the uniform convergence. So the distance is measured throughout the domain at the same time, and that the domain maximum of that has to go to 0. Okay. So on the left we do it one point at a time. Okay. So to why it is not uniform convergence, once again, remember that how we're supposed to fit our the sequence, or at least the tail of the sequence, within a certain band around the limit function. So if that at the bottom it is my limit function, then we have to fit the sequence or the tail of the sequence within this band. Okay, so it is quite clear that it won't fit. If I pick any band, say less than width less than 1, so say 1/2, so that tooth will always stick out. Okay, so it's not going to converge in a uniform way because the distance will be always equal to 1. On the other hand, there is that we demonstrated, or at least it's seemingly convincing idea that there is a uniform, there's a pointwise convergence on the left. Okay, so one point at a time, which is, maybe if I can find that picture. Oh, here it is. Okay, slightly better picture, and you can see. So it's the tooth is getting narrower and narrower with the same height. Okay, so you could try to what? I mean, if you want to do it dynamically, that's what I'm thinking. If I the sequence is kind of short, so maybe what? Okay, okay. So if I put it, what's going on here? Okay, you can see kind of a dynamics of what's happening here, right? Rather than drawing them one by one, what if I overlap them? And you can see the dynamics. Okay, so the tooth is the tooth is not moving as much. It is, like I said, is narrowing. At the same time, that flat part of the graph is widening. Okay, so you could in fact did I do it right? Roughly, it is more or less close to the truth. You can try. Okay, let me try it. Okay, so, oops, no, wait a minute. Okay, so, yeah, I was trying to illustrate this in a dynamical way, but it is not that simple. Okay, let me try again. So if I put it here and here like this, so we would have to then be watching the okay, so once again on the right is you can see how dynamically that sequence of functions is progressing. Okay, so once again the tooth is getting narrower and the flat area getting wider. Okay, and then which means that if I would ever point a pick on that flat area, then which might not be flat necessarily, it will be eventually there. So if I start with over here, anywhere like that, like this. So if this is my x, and the value is, I don't know, maybe 1/2 the value of the function. But if I keep doing it, it might even increase at some point like this. It's close to 1, okay? but then will be on the narrow side, so it may be 1/3, whatever, and then, but it is then inevitably will become 0. Okay, so the value of, at that particular value of x, one fixed value of x, what's happening? 1/2, 1, 1/3, 0. Okay, so you can imagine that if you have more points, more intermediate points, you will have a nice graph. Okay, so so once again, let me describe this in words. So pointwise convergent, but not uniformly convergent. Okay, the truth. The other example, and it is defined on an interval. The other example that we did yesterday was something that looks more natural as far as convergence is concerned, but also pretty much the same example. So this is example here, and that there is another example of the same thing elsewhere, which we did yesterday, and that was the convergence of a Taylor series of the exponential function. And uniform convergence only holds within the interval, but not outside, not on the whole real line. Okay, so so there is no gap if you keep the interval intact and not expanded. Then there is no gap, and the functions are virtually indistinguishable. And if you make a bigger gap, you will just have to wait longer in order to see that they are indistinguishable. But if you simultaneously start convergence on the whole thing, then it's not working out anymore. So Tn converges to f, Taylor series of the function, uniformly on any interval AB within the domain of f. Naturally, but not on R. Okay, well, in fact, probably makes sense to actually start with pointwise convergence. So, so Tn converges to f pointwise on R. Okay. It is also uniformly converges on every interval, but it does not converge uniformly on R. Okay, so these gaps that I demonstrate in yellow, they will always be there, no matter how many steps you try to make. The two functions will always run away from each other because of exponential nature of the because of the horizontal asymptote of the exponential function. And so while the polynomial always goes to infinity, this one has a horizontal asymptote. So there cannot be you cannot possibly fit. Now let's make that clear. You cannot possibly fit no matter how many steps you make. You cannot fit your function into this band. Well, sorry, that's not the right one. The band that I was talking about was the band around the original function. So if I put this what a band would look like. A band around our function that's supposed to be the limit. Okay, now imagine, can you fit a polynomial in this function all the time? It definitely, on the right it might take some explanation why it is impossible, but on the left is definitely not impossible, because every polynomial will eventually go to infinity like this. Okay, that's the nature of polynomials. On the right, also there will be a gap. Why? Because why? And no polynomial can stay within this band on the right of the y-axis.
Does an exponential function grows quicker?
Yeah, exactly. Okay, so it will drop out here somewhere. Okay, so will drop out here somewhere or there. It either goes to one infinity or the other infinity. On the right, it will inevitably go. It will just cannot keep up with the exponential function. Okay, then we cannot have uniform convergence. Another example of the same thing, I just happen to have, just a minute, another one, the trig function. I have somewhere, where's my trig function? Here it is. This is cosine, and the story is the same. So my cosine is that blue function over there. But if I try to create take a band around it like this, right? You see it? Then the question once again becomes: can I fit polynomials within that band? I cannot. Why? Because once again, the same story. The exponential function, the polynomials will go to infinity eventually, while cosine is bounded. Okay, so eventually, you can see it on that picture, the Taylor polynomials, how they approximate, but eventually they will drop out of that band. Okay, so you can see quadratic cubic polynomials, they get better and better, right? The orange one is, you can see, the fourth degree polynomial is actually fits longer, stays longer within the band, but eventually it will drop out. Okay, so that is something that that's advanced calculus for you. Okay, so hopefully you'll take that at some point. So more profound, but more deep look at the calculus, calculus of functions. So it's also sometimes it's called not advanced calculus, but rather functional analysis. So analysis of spaces of functions. Okay. Okay. So as you can see, once again, so one statement here I made that about two things with two examples from calculus of what can or cannot happen in this space of this metric space of functions. The metric space of function is also problematic whenever we look at R, because even though functions are continuous, they not necessarily reach their maximum value. So I subtract, and then the actual maximum might be infinite easily. Okay, so that's another problem. But the main problem is actually kind of a hidden one, and that is the discussion of metric space versus what? The uniform convergence comes from a metric space. This one. Okay, the one that we define, that is d that I have over here, is the distance between functions, and those functions form a metric space. We proved it. Okay. However, and then that metric space, if you look at convergence of functions within that metric space, it gives you a uniform convergence, something familiar from calculus. Okay, pointwise convergence then is there a metric space for the for pointwise convergence? That's the question. So is there a metric for, say, CR that gives us pointwise convergence? So once again, it is, the answer is whenever we talked about uniform convergence, and then is there a metric that gives uniform convergence? The answer is yes. Okay, so that's what we have demonstrated. But to this one, the answer is no. Okay, so there cannot be no metric for that, for pointwise convergence. So once again, all the convergences that we have seen are actually pointwise convergences. If you go with the big domain, so Taylor polynomials converge to the function pointwise. Okay, so and that we would like to have that space of all functions that reflects pointwise convergence somehow, and then there is no metric for it. So what is the way out? And the way out is go even more general. So and that is where topological spaces come into play. So use topological spaces instead. So topological spaces are generalizations of metric spaces. So we go from where we were in calculus, and we want to understand functions as a whole. and the distances between them, like functions looks very big. As you start studying functions, they look very big. I mean, many numbers, some rule, and so on, and then there's a graph, and then you sort of start flying higher and higher, and then there are many functions to look at the same time, and then they become looking like dots on like if you're flying on a plane, the people look very small, and then cities look very small, and so on, and you look at the whole thing as like it's a map. Okay, so that's how we are working out. We're doing it, except now the distances do not work anymore. Which is how is it even possible not to speak of convergence of sequences and other things topology related, such as connectivity, continuity, and so on. You can imagine that it's like imagine the world that used to be the case. It's still the case where there are distance standards for measuring. So we're using miles here, and over there we use kilometers. Okay, so different standards. So in that sense, if we ignore the possibility of making the transition or the conversion of the units, there are, suppose you don't know anything about kilometers. Okay, so it is still not a problem. They are able to measure distances over there in some mysterious to us way in Europe, say, and they are doing just fine. Okay, so there is no need really for any comparison. Imagine that our interest is local right now. We're looking once again at this idea of convergence to a function, to polynomials to a function. So it means that we have, so if this is a function, we want to understand how to say f, and we have a bunch of tn's convergent to it. Okay, but somewhere else, a function might be entirely different, like this. And then once again, we have a convergence of tn to f. But these two, this function f and this function, well, let's actually call it g, they're far apart from each other. Okay, so there is no need for them to actually, there is no need for us to know the distance between f and g. All we care about there, when we need f, we're measuring distances in one way, and when we are looking trying to approximate g, we're using distance in another way. Okay, so why would we? We cannot be simultaneously in two places at the same time. So for example, you are measuring everything here in miles, and whenever you go to Europe, you can just if you forget for that duration of the trip anything about miles, you will be just fine measuring distances in kilometers. Okay, and then you can imagine that you can throughout every country or every location has their own different way of measuring distances. And that's just fine. Once again, you cannot simultaneously be in two places. And so once again, we don't need to know the distance between f and g. We only care about the distance between these two, d, t, and f. That's the only distance we care about. Okay. So how do we get out of it? And the answer is. Like I said, it's called topology. So the structure on a set, which is structure of metric x and d, a metric space. As you can see, it is even though abstract, it's not really that abstract because this is a real valued function. A very convenient function because it uses our understanding of or intuition of distances. And now it appears that we cannot really rely on that anymore. And the answer is to make that step towards topological spaces, is to see what is that metric spaces produce. And the answer is that metric spaces produce balls. Okay, and those balls, the set of all balls, that's all we need. Okay, and that reflects the idea of separate ways of measuring things. So for example, I could speak of convergence here. That is one way, and that is the word that is being used is a neighborhood. A neighborhoods or open sets. Okay, so so then now think about the word neighborhood is kind of descriptive because it tells you what functions are in the vicinity of the, or what elements are in the vicinity of that particular point and nothing else. So for example, if your function g is constant as there, then what functions are in its vicinity? And well, there are a bunch of them, but they are not the same as these. So this is the vicinity or neighborhood around F is this. Okay, and once again, these two are unrelated to each other. You can imagine the first one is America and the second one is Europe, and you measure distances in an entirely different way. It doesn't matter, and they might not be compatible with each other as numbers. But well, how do you combine them together? That's how. You take all the set of balls from here and set of balls over there and put them together, and that will allow you to consider convergence, which is what we are after. So so once again, x n converges to x, and now it is not. We can rewrite it without referring specifically to the distance. So here's how it goes. Well, let me write the original definition in the metric space. In a metric space, xd. So what is for every epsilon? There is n such that n larger than n gives me, what is it, dx n x less than epsilon. Okay, so that's the original definition. But now what we're talking about is replacing that the distance with replacing the distance over here with just saying that xn belongs to, what does it belong to? Well, does it mean that distance between xn and x is less than epsilon? These are balls we're talking about. So it belongs to b x epsilon. Okay. So an epsilon ball around x. Okay, so those little strips that I drew there, these are the balls that are supposed to contain the tail of the sequence. Okay, so I can restate this as follows. I could say that for every ball around x, and then follow on the same, there is n such that n larger than n, we have xn belongs to b. For every ball b, like this. Okay, so that is the same statement, except epsilon is kind of has disappeared. So for every ball, strip, whatever you prefer, disk, whichever way you prefer to call this. So every ball around x, no matter how small, there is an n such that the tail of the sequence past that n capital will belong to that ball. Okay? So then if you think about it, at that point the idea of the ball is really becomes not that important, and we have seen the different kinds that there do not look like anything like a disc or a ball or a sphere. So even though we would illustrate it in this manner, right? So this is my a over here, x over here, and this is my sequence, right? xn. Eventually, it is within that ball b. But why do I draw it around anyway? We don't even know anything about the nature of that metric space anyway. So maybe it looks like this. Okay, my x is here. Okay, and then the idea is the same. The sequence should be eventually inside of this I keep calling a ball, but really it could be anything of nature. Even with taxicab metric, remember those it's two-dimensional. They're supposed to be disc, but they look like squares, like this. Okay, so the shape of those balls is not only irrelevant; it is simply not even an issue to worry about. Because there is no such a thing as shape in topology. We're only looking at we define them as balls because we use the word as a way to utilize our intuition about distances. But the balls could look like that. So once you replace the word ball with the word neighborhood, it becomes clearer what we're talking about. So if in the standard case of Euclidean Rn, and I could I have a sequence, not a sequence, but rather the whole bunch of balls around the point, right, like this, of any as small as you like. Okay, and that what allows me to discuss convergence, because there's a whole I can always pick the smaller ball around the disk, in this case, small and small around B, and then force and make sure then that the tail of the sequence is inside of that disk. Okay, but it doesn't really matter what that shape is. Imagine that. What can we imagine? Say I have an X here, and what kind of neighborhoods hypothetically you can have? Well, we already know that you can have squares this way, you can have squares the other way. So once again, like this, and once again we have the same idea continuing on. I could have well, once again going with the taxicab metric. So you can have, this is just as good. Once again, the picture, either the original picture on the left or these two, you can discuss convergence of a sequence to that value x, because once again you can always pick smaller neighborhood of that point, and then once again everything is supposed to end up there. I don't know, stars like this. The shape doesn't matter whatsoever. It is still working just fine. So imagine this. So once again, you can make these as small as you like, and once again the convergence still makes sense. Okay. So once that is understood, we can feel free to discuss topology without even a mention of numbers, which is what the definition of convergence here is. It relies on. It still relies on the distance, and the distance is a number, and then there's that epsilon. Instead, we rely on just some kind of subsets. These neighborhoods I speak of, they are nothing but subsets of my set X. Okay, so and the shapes, once again, it's not even an issue to worry about. And once again, the intervals on the straight line. So then the question only remains now: what kind of set of subsets would still make sense in order to create something that is just as good as a metric space for dealing with things such as convergence of sequences, limits of functions, continuity of functions, connectedness of sets or spaces, and so on. The definition is still almost as compact, or even more compact than the definition of a metric space. So this is the definition. So X is a set. Tau is a subset. Is a set of subsets of X. Okay. It is called a topology on X if the three axioms are satisfied. Number one, the empty set in the X belong to tau. Okay, so so when X is, you remember these sets are supposed to give us a kind of a measure, non-numerical measure of closeness of points. Okay, so we cannot, there is no metric, there is no measuring stick anymore. Okay, so how do you well, think about it like this. Once again, if you take a trip to Europe and you are not able to measure distances anymore, so how do, and you don't even know what kilometers are, so how do they accommodate you? Milestones, no, not kilometer stones, if you prefer. So even though you don't know what kilometer is, those markings will tell you how far you're going, or how close you are, rather, to a particular destination. So and then, you know, if you see that those numbers are getting closer to zero, for example, you know that you're approaching a city that you are trying to arrive to. Okay, so then those milestones are not strictly speaking about distances anymore, but rather about the closeness towards of your location to a particular, to your destination. So you're arriving to a certain city. It doesn't really matter. So this city may be using miles, and this one uses kilometers. That doesn't really matter. They will tell you if you're approaching that city. You will know that that's happening as you see those numbers getting smaller and smaller, even though the units might be totally unrelated. Okay, so then x is the measure of closeness, which is kind of gives you exactly zero information. So it is a starting point. There are 2 and 3. UV belong to tau. Then the intersection belongs to tau. And number 3, you have a whole family, possibly infinite. So say alpha is a subset of tau, then its union of that family belongs to tau. Okay. And once again, so these properties, or rather axioms, would have to be explained, but they're explained very simply if you with a certain experience that you had in calculus 3, possibly it is the open sets in R. Say, let's just take open sets in R2. Open sets in R2 satisfy these properties. Okay. So first of all, what is an open set? So I'll get back to this definition, which is abstract and takes time to digest. But let's see where we have seen something like that. And whatever Euclidean space you pick, there is such thing as open set, and then that set of all open sets will satisfy this property. So well, first of all, what is an open set in R2s? Let's say. You remember what that is? Open sets. Well, to begin with, all open disks are open sets. Okay, so like this. So this is my A, and then the one that does not contain its boundary. That's what makes a disk open, or a ball, is that it does not contain its boundary. So this U is equal to those x. The distance to A, let's say A, is less than R, strictly less than R. Okay? Strictly less than R. So that's an example of an open set. An example of an open sets. Do you remember how you use disks in order to define all the rest of the open sets? What makes it open? So why is this some shape which is not round anymore, but as long as that boundary kind of is not included, then we have an open set. So what makes it open? Without using the word boundary, that's the thing about it, is that the idea is that we do want to use eventually sequences or boundaries or anything like accumulation points, limit points, whatever, they come from this set of axioms. So we want to right now concentrate entirely on open sets and use to define open sets in this on the plane using nothing but the balls, okay, or disks rather. So how do I use, if I know that this is my open disk, how do I make sure that this, how do I define this open set as opposed to, well, what makes it, how do I make this set not open at an extra point over here, and it's not open anymore? So if all the points on the boundary are excluded, then I have an open set when at one point it's not closed anymore. So why? In what sense it's not closed? Rather, in what sense it's not open anymore? Well, let's take once again, the only tool we're allowed to use right now is those disks. So I look what is so special about this point. So that's the question. So let's say I pick point X over here, and I pick that green one. I call it a Y. Okay. So what is the difference between X and Y? So X and Y are points. So once again, X point in blue and Y point in green. What is so special about their difference of their locations expressed in terms of disks? Disks around that point.
You couldn't make a disk small enough around Y to be included in the...
That's right. That is the answer. So if I choose a number small enough and I put a disk around X, it will fit in entirely inside of this set, say V. Okay. However, it is impossible to do if I try to do it around Y. No matter how small my disk is, it will stick out. Okay. So once again, that's what makes and that's what makes the difference between open set and not open set. It is the presence or absence of such a point that would not cannot be separated from the outside by disk. So I can separate X from the outside of V with a disk, but not so much, and then it's impossible with Y. Okay, so if you prefer to use the well, okay, let me write it up. So V is open when for every X in U there is an R such that BXR lies entirely within B. Okay. So as you can see, the way it is written, it has nothing to do with disks. You can think about whatever your metric space you pick. That will be still, it will still work, because in metric space, if you have metric space, we have a distances, we have disks or balls, and then we can have this definition of open set. So it certainly applies to all Euclidean spaces. Two-dimensional Euclidean space that we're using disks, a three-dimensional ball, one-dimensional intervals, and so on. And that's the idea of open sets. Okay, so they do come up a little bit in Calculus 3 for certain things, but not a lot. Okay, so but that's an open set, and this is then let's take the collection of all open sets. So this is the way we are proceeding is tau is equal to V open in say R2. Okay, so then this one certainly is here. That one satisfies the property. This one includes all the balls, but also there are certainly open sets that are not balls. You can take two balls, put them together. For example, if I have one open ball like this, Okay, I take another open ball like that. I can put them together, and what can we say about the result, about this? The green one, two open balls put together as the union. What is this green thing? What can you say about the green set?
Still open?
Yeah, it is open, yes. Okay, so two open set put together, it gives you still an open set. You can pretty much demonstrate that. It would take a theorem, by the way. Well, let's prove it. It's not really that bad. So UV open, then U union V open, based on our definition. Based on this definition that we're looking at. So, okay. Well, this takes some, the use of the definition becomes crucial because, once again, we are building something from scratch pretty much, and we're dealing we're going to be proving things for metric spaces for the time being in order to then proceed to topology. But at this time, we are living in a metric space. We define open sets in terms of the balls or distances in the metric space, and we want to try to prove some theorems about those properties of these sets. So, okay, so I'm going to use the definition of openness, this one, 3 times, right? So U is open, V is open. We need to show that the union is open. Okay, shouldn't be too hard. Okay, so U is open, and you just keep writing. Means that once again, for every x in U there is a R such that BXR is in U. Okay, and then I have V. I'm writing the exact same thing. Ends in V. Okay, so putting these together, these two statements I'm putting together. Okay, so what can I say? I take these two statements, the right part of these two statements that starts with for every x. Well, let me write out anyway. For any x in V, there is a, and here I want to use a different letter, s greater than 0, such that Bx s is a subset of V. Okay, so let's take those two statements to the right and put them together. So for every, let's write out for every, I intentionally use the same letter x here. For every x in U, and for every x in V. Well, I don't really, I'm looking at it, I don't really see what is that to be proven here. You see it? So for every x in U, so we have two sets and another set, U and V, I pick a point. I can separate it from the outside with a disk. Okay, so if it is in U, what if it is in V? Same story. I can once again separate from the outside with a disk. Okay, so and now every point in X in the union of these two sets will be we can use either one or the other in order to separate from the outside, or in other words, is the complement. Remember. So outside to separate that point from the complement of the set, and we have it here. Okay, so let me just write out. I'll put a union here, union V. There is R greater than 0 such that BXR is in U, or BXR. Well, actually, it's not or, it's in. BXR is in V, which means, I mean, that BXR lies in U, or it lies in V in the well, it is or here, because we don't know to which one of the two X belongs to. If it belongs to U, then we're using number 1. If it belongs to V, then we use the other one. Or they might belong to the intersection, then we pick one at random. So, but regardless of what it is, that disk around X will lie in the union, right? So it lies in U, or it lies in V, which means that it will lie definitely, no matter what, it will lie in the union of the two. Okay, so that picture on the left it illustrates the proof on the right. Okay, so union of two open sets is open. It is really the proof is not just straightforward. It is kind of I would say a proof by examination. It is the challenge is a slightly more challenging proof if we take the intersection. If we take the intersection of two sets. Okay, so we still have to prove that the intersection of two open sets is open, and that is the well, let me copy and you point out what we need to modify. Okay, so what I'm doing is I'm replacing union with intersection. Okay, so then we are talking about now this piece, U intersection V. Okay, so this part is the same. So still, U is open, V is open, which means that for every X we have this property satisfied. And so this transition becomes impossible now because we cannot we are not. It's not enough to say that disk that we're supposed to find lies inside of the union. It has to lie inside of the intersection. So okay, so once again intersection here. Okay. So what's the idea? How do we find if there's actually a point that we're talking about here lies in the intersection? If it lies in the intersection, then it can be separated from the complement of U and from the complement of V. How do you separate it from the complement of the intersection? I guess we're out of time. Okay, so we'll do it next time.